All right, so get ready, because today we are diving deep into structuralism in physics.
Ooh, that sounds intriguing.
It is.
Right.
And, it might sound a little bit like mixing, oil and water,
Yeah.
but it's a really fascinating area, especially for, well, a philosophy enthusiast like you.
Okay.
And for this deep dive, our guide, our
Mhm.
ultimate cheat sheet, is going to be the Stanford Encyclopedia of Philosophy.
Nice.
Have you ever, just thought about how physics theories, even the ones that are like super fundamental,
Right.
they kind of dance around certain terms.
Mm-hmm.
They never quite, really define them.
Like they're built on these conceptual quicksand patches.
Exactly.
Yeah.
And that's exactly where structuralism comes in. It's like it's trying to give us some solid ground to stand on.
So instead of getting bogged down in like what these tricky terms actually mean, structuralism is looking at the relationships between them,
Oh,
the structure they form.
so it's less about the individual pieces and more about how they connect to
Exactly.
create the whole picture.
Precisely. And it's actually fascinating that this structuralist thinking,
Yeah.
it isn't just limited to physics.
Right.
You see it in linguistics when you're analyzing the structure of language, even in anthropology, looking at the structure of societies.
Oh, interesting.
It's this underlying pattern of thinking that we can apply to all sorts of complex systems.
So how did physicists actually get on this path?
Hmm.
Was it just like a sudden eureka moment,
I-
or was it something that kind of developed over time?
It's more of a gradual evolution of thought, I would say. Even
Yeah.
back in the 19th century, you have physicists like Heinrich Hertz, and they were already wrestling with the question of how our mental models of the world connect to the actual workings of nature.
Wow.
So he said, and this is a mouthful, we form for ourselves images or symbols of external objects, and the form which we give them is such that the necessary consequence of the images in thought are always the images of the necessary consequence in nature of the things depicted.
Okay, so let me see if I'm unpacking this correctly. He's basically saying that, like, our theories are like blueprints.
Mm-hmm.
And if the blueprint is accurate,
Yeah.
then what we think should happen based on that blueprint,
Yeah.
like, will actually happen in the real world.
You got it. And structuralism is all about taking those blueprints, our theories, and figuring out how they're constructed,
Right.
what rules they follow, and what they can and cannot tell us about the universe.
Okay, that makes sense.
Yeah.
But how do you actually apply this structuralist lens to something like physics?
Right.
I mean, where do you even begin?
So let's start with a classic example. Newton's second law of motion, the famous F equals ma.
Oh, yeah.
Force equals mass times acceleration.
By Physics 101.
Right,
yeah.
exactly. But here's where it gets a little bit tricky. How do we define what force actually is
Right.
without ending up in a circular definition?
Mhm.
Like if we say force is that which causes acceleration, then our equation becomes a tautology. It's just saying the same thing twice.
So it's like saying a bachelor is an unmarried man. It's technically true, but it doesn't actually tell us anything new.
Exactly. And this same issue pops up with mass as well.
Okay.
If we try and define mass using the same equation, we end up defining two things with one equation, which logically it just doesn't add up.
So how do we escape this circularity?
Right.
Do we just like throw out Newton's laws and start over?
Not quite. So
Mhm.
one way to break free is by adding more laws into our theoretical framework.
Okay.
For instance, if we specify that all forces involved are gravitational, we can actually define them independently using Newton's law of universal gravitation. This gives force a meaning outside of F equals ma.
So it's like adding more pieces to the puzzle
Yeah,
so that the picture becomes more clear.
exactly.
Yeah.
And we can also equate inertial mass, the m in F equals ma,
Yep.
with gravitational mass, which we can measure independently.
Oh, yeah.
By adding more context and connections, we give those terms independent meaning.
That makes sense.
Yeah.
But I have a feeling this isn't the end of the story.
You're absolutely right. There's another wrinkle.
Uh-oh.
The acceleration we're talking about is implicitly assumed to be measured relative to an inertial frame of reference, which basically means a non-accelerating viewpoint.
Okay, why does the viewpoint matter so much?
Yeah.
Doesn't acceleration just mean like speeding up?
Well, imagine you're in a spaceship and you are accelerating upwards.
Okay.
From your perspective inside the spaceship, a free-floating object
Yeah.
would appear to be accelerating downwards, even though there's no actual force acting upon it.
Oh, wow. That's kind of trippy.
Yeah, so the same physical situation can look totally different depending on where you're standing.
Or flying in this case.
Exactly. And what's even wilder is that this apparent downward acceleration in the spaceship acts exactly like a gravitational force.
Oh.
Its magnitude is proportional to the object's mass, just like gravity.
So how do we tell the difference between like real gravity and just the like weirdness of our viewpoint?
Great.
Seems like things are getting pretty slippery here.
That's where things get really interesting, and that's where structuralism really comes into play.
Okay.
We have to carefully analyze the relationships between these concepts like inertial mass, inertial force, and gravitational force, all within the context of the theory itself.
So it sounds like what you're saying is that structuralism is like a philosophical tool that helps us untangle these messy conceptual knots in physics.
Precisely. And remember, this whole issue of potentially circular theoretical terms
Yeah.
isn't limited to classical mechanics. It pops up in almost every fundamental physics theory, from electromagnetism to quantum mechanics.
Okay, so structuralism seems like a pretty useful tool for any philosopher brave enough to, dive into the world of physics. But it sounds like there's more than one way to approach this, right?
You're catching on quickly.
Okay,
There are actually three main approaches to structuralism in physics,
good.
each with its own unique flavor and set of tools.
Ooh, tell me more.
All right, so we've got a fascinating trio of thinkers, each bringing their own perspective to the table.
Okay.
First up, we have Joseph Sneed, the model guy.
Okay.
He loves using the tools of set theory to build a rigorous framework for analyzing theories.
So Sneed is kind of like the architect of structuralism.
Yes, carefully mapping out the blueprints.
Okay, so we've got Sneed, the architect, setting the stage. Who else is on this structuralist dream team?
Next, we have Günther Ludwig, the axiomatic guy.
Okay.
So if Sneed is the architect, Ludwig is like the logician making sure that the foundations are rock solid.
Gotcha.
He's all about finding the most basic assumptions, the axioms, and building the theory up from there using pure logic.
So he's not just analyzing the existing theories.
Yeah.
He's actually like trying to reconstruct them from the ground up, using logic as his building blocks.
Exactly. And by doing so, he avoids those circular definitions that we were talking about earlier.
Right.
He defines everything within the framework of those axioms, so there's no room for any ambiguity.
So it's like he's creating his own self-contained logical universe.
Right.
Okay, so that's two very different approaches. Who's our third player in this?
Last but not least, we have Erhard Scheib, the pragmatic guy.
Okay.
He's less interested in building these grand formal systems and more interested in understanding how theories actually work in practice, how they evolve and relate to each other over time. He's like the historian of the group, looking back at the development of physics and tracing the lines of influence.
So he's more about observing the real-world, messy process of science, rather than trying to create a perfect system.
Exactly. And one of the things that fascinates Scheib is this idea of reduction.
Okay.
How one theory can be seen as a special case of a more general theory.
Can you give me an example of that? Like, how does one theory reduce to another?
Sure. So think of classical mechanics and relativistic mechanics.
Okay.
When objects are moving much slower than the speed of light, the equations of Einstein's relativity, they kind of simplify, and you get back to Newton's equations.
Oh.
So in a way, Newtonian mechanics is reduced to a special case within this broader framework of relativity.
So it's like zooming out to see the bigger picture.
Right.
And that old theory is still there. It's just kind of nested within the new one.
Exactly.
But you said that Scheib sees this process as messy. What did you mean by that?
Well, Scheib emphasizes that this reduction process isn't always a clean and perfect fit.
Okay.
There might be concepts that don't translate perfectly from one theory to another,
Okay.
or leftover bits and pieces that don't quite fit into the new framework.
So it's not always as simple as just plugging the old theory into the new one.
Right.
There's some wiggling and adjusting involved.
Exactly. And that's what makes Scheib's approach so interesting.
Yeah.
He recognizes that scientific progress isn't always this linear, straightforward march towards the truth. It's more like a winding path with unexpected twists and turns.
This is reminding me of something we talked about earlier.
Yeah.
About how physics seems to dance around defining certain terms.
Right.
How do these three structuralist thinkers actually address that problem?
Great question. Let's start with Sneed.
Okay.
His approach is all about creating these things called model elements.
Okay. Model elements. That sounds intriguing. Break it down for me.
So imagine you have this giant Lego set
Okay.
that represents a physical theory.
Right.
Each model element is like a specific set of those Lego bricks, along with instructions on how they fit together.
So it's like a miniature version of the theory built with conceptual Legos.
Exactly. Now, each model element has two main parts.
Okay.
First, you have the potential models,
Okay.
which represent all the possible ways that those Lego bricks could be put together.
So it's like saying, here are all the Lego pieces you have, and theoretically you could build anything you want with them.
Precisely.
Yeah.
Then you have the actual models, which are the specific configurations that actually satisfy the laws of the theory.
So the potential models are like the theoretical possibilities.
Right.
And the actual models are the ones that match up with reality.
Yeah.
Or at least with how the theory describes reality.
You got it. And Snead adds another layer to this.
Okay.
He introduces constraints,
Okay.
which are additional rules that connect different models within the theory.
So it's like saying, okay, you can build whatever you want, but all the red bricks have to be the same size. Or something like that.
Exactly. These constraints give the theory more substance, more specificity. They help us rule out certain possibilities and say, within this theory, these elements have to behave in this particular way.
Okay. I'm starting to see how this all fits together.
Yeah.
But how do Snead's model elements actually help us with those pesky undefined terms?
That's where those Ramsey sentences come in.
Okay.
Remember how we talked about rephrasing theories to avoid explicitly defining those tricky terms?
Right.
That's essentially what Ramsey sentences do.
Okay, so can you give me like an example? Like how would you rephrase something like Newton's law of gravitation using a Ramsey sentence?
Sure, so instead of saying force equals gravitational constant times the product of masses divided by the square of the distance,
Right.
we would say something like, there exists a number and there exist properties of objects such that.
Okay.
And then we describe the relationships between those things without actually saying what they are.
So it's like saying, we don't know exactly what these things are,
Right.
but we know how they behave and how they relate to each other.
Exactly. It's a clever way to sidestep that circularity problem by focusing on the structure of the theory,
Right.
the relationships between the elements, rather than getting bogged down and trying to define each element individually.
Okay, that's pretty ingenious.
Yeah.
Okay, so that's how Snead tackles this problem.
Right.
What about Ludwig?
Yeah.
How does his axiomatic approach deal with those undefined terms?
Ludwig's approach is all about precision and clarity.
Okay.
He defines all the theoretical terms within the framework of the axioms, the starting assumptions of the theory. It's like creating a dictionary for the theory, where every word has a very clear and unambiguous meaning based on those fundamental axioms.
So there's no room for any wishy-washy definitions.
Yeah.
Everything has to be logically derived from those core principles.
Exactly. It's like building a house on a solid foundation. By defining those terms so rigorously, Ludwig avoids that circularity trap completely.
Okay, I'm starting to see the beauty of this axiomatic approach.
Yeah.
It's all about building a system where everything is perfectly interconnected and defined.
Right.
So what about Scheib? He seems to be more about the big picture, the messy realities of science.
Right.
How does he approach those potentially circular definitions?
Well, Scheib is less concerned with creating a perfectly defined system and more interested in understanding how theories relate to each other. Remember his focus on reduction.
Mm-hmm.
He sees this process as a way of clarifying the meaning of those theoretical terms.
So by seeing how one theory fits within a more general theory, we gain a better understanding of what those terms actually mean.
Precisely. Let's go back to the example of classical mechanics and relativistic mechanics.
Mm-hmm.
By seeing how those Newtonian concepts like force and mass transform within the framework of relativity,
Yeah.
we gain a deeper understanding of their limitations and how they relate to these more fundamental concepts.
It's like seeing those terms from a new perspective, understanding how they fit into a larger puzzle.
Exactly.
Okay, I think I'm starting to get a handle on how these three thinkers approach the problem of defining these theoretical terms.
Right.
But it sounds like they're all coming at it from very different angles.
Yeah.
Did they ever interact with each other's ideas, or were they just kind of working in isolation?
That's a great question, and it might surprise you to learn that even though their programs develop separately,
Right.
there's clear evidence of influence and cross-pollination between these approaches.
Really? So it wasn't just three guys in their own philosophical silos completely ignoring each other.
Not at all. There was a real sense of intellectual exchange, even if it wasn't always explicit. For instance, Snead and his collaborators, they later incorporated Ludwig's concept of uniform structures into their own framework.
Okay, back up a second.
Yeah.
What are uniform structures in this context?
They're a bit technical, but essentially they provide a mathematical way of describing approximations.
Okay.
An approximation is a key concept in Ludwig's approach because he recognizes that our theories are never perfect reflections of reality.
Hmm.
They're always approximations.
So Sneed's saw the value of Ludwig's tools for dealing with this inherent fuzziness of scientific theories.
Exactly. They realized that even with their rigorous model theoretic approach, you can't escape the fact that our theories are always simplifications of a much more complex reality.
It's like even with the most precise Lego instructions,
Right,
you're still dealing with plastic bricks, not the real thing.
exactly.
So what about the other way around? Did Ludwig ever borrow anything from Sneed?
He did. Ludwig later added a section on theory nets to his work,
Okay.
which draws heavily on concepts developed by Sneed and his colleagues. Theory nets are basically collections of those interconnected model elements, organized by this sort of hierarchy of generality.
So Ludwig saw the value of Sneed's approach for describing the relationships between different theories,
Yeah.
how they kind of fit together in this larger framework.
Exactly. It's a beautiful example of how, even though these thinkers had their own distinct perspectives,
Right.
they were still learning from each other, refining their ideas through dialogue and debate.
And what about Scheib? Where does he fit into this intellectual exchange?
Scheib, being the pragmatist that he was, often acted as a commentator,
Okay.
providing insightful critiques and comparisons of the other two approaches.
So he was like the referee, making sure the conversation stayed honest and productive.
Exactly. And through these interactions, through this back and forth, the different approaches to structuralism have continued to evolve and refine themselves.
Mhm.
It's this ongoing conversation, this quest to understand not just the content of our physical theories, but the very structure of scientific knowledge itself.
This is all so fascinating.
Yeah.
But before we get too carried away, can we take a step back and just recap the key differences between these three approaches? I want to make sure I'm keeping them all straight.
Huh.
Okay, so let's do like a quick review here.
Yeah.
We've got Sneed, our architect,
Mm-hmm.
building those intricate model elements
Mm.
with his, trusty set theory tools.
He's all about creating this formal system, that captures those relationships between different concepts in a theory, using those clever Ramsey sentences to avoid getting stuck in those circular definitions.
Right, right.
Oh, yeah.
And then we have Ludwig, our logician, laying down the law with his axioms,
Yeah.
making sure that everything's defined with, like, absolute precision.
Ludwig's approach is all about rigor and clarity, building a system where the meaning of every term is just crystal clear, derived from those fundamental axioms.
Yeah. And finally, we have Scheib, our
Right.
pragmatist, taking more of a historical view,
Yeah.
focusing on how theories actually evolve and connect with each other in the, messy real world of science.
Scheib's fascinated by this idea of reduction, but he sees it as this complex and nuanced process, not always a clean and perfect fit.
Right.
He reminds us that scientific progress isn't always a straight line.
Okay, I think I'm starting to see the big picture here.
Yeah.
But I have to ask, out of these three approaches,
Mm-hmm.
which one really resonates most with you?
That's a tough one. Each approach has its own strengths and weaknesses,
Yeah.
but I think, personally, I find Scheib's perspective particularly thought-provoking.
Okay.
His emphasis on the incompleteness of reduction raises some really profound questions about the nature of scientific knowledge.
I see what you mean.
Yeah.
If reduction is always incomplete, does that mean that physics will always be a work in progress?
Right.
Forever chasing after that final theory of everything but never quite reaching it?
That's one way to look at it. Or perhaps it suggests that there might be multiple equally valid ways to picture reality, each with its own strengths and limitations.
So instead of searching for this one ultimate theory,
Right.
we might be better off kind of exploring a tapestry of these interconnected theories, each illuminating a different aspect of the universe.
Exactly. It really challenges this notion of a single absolute truth in physics and suggests a more pluralistic view of scientific knowledge.
Yeah.
And that's something I find really exciting.
This deep dive has definitely given me a lot to think about. So for our listeners who are, eager to explore this further, where should they turn?
Well, the Stanford Encyclopedia of Philosophy article we've been using is a really excellent starting point.
Yeah.
It provides a really in-depth overview of the different structuralist approaches and their nuances. And, you could also delve into the works of other prominent structuralist thinkers like Wolfgang Stegmuller, C. Ulysses Moulins, Robert Balzer.
Right.
They offer some really fascinating perspectives on this whole idea of how we structure our knowledge of the physical world.
Fantastic suggestions. So as we wrap up this exploration of structuralism in physics,
Hmm.
I'm left with one final thought-provoking question for our listeners.
Okay.
If Shaibib is right, and reduction is always incomplete, does this mean that our quest to understand the universe will never truly be finished? Are we destined to be, forever exploring, forever discovering, but never reaching a final destination?
I think that's the beauty of science and of knowledge itself.
Yeah.
It's a journey, not a destination.
Right.
Structuralism gives us this framework for appreciating the complexity and the interconnectedness of our scientific understanding.
Yeah.
But it also reminds us that there will always be more to discover, more to learn, more to explore.
Absolutely. It's like we're setting sail on this endless ocean of discovery.
Yeah.
And who knows what wonders we might find along the way. Thanks for joining us on this incredible journey into the world of structuralism in
It's
physics.
been a pleasure.
Until next time, keep asking questions and keep diving deep.